So last time we proved this very interesting theorem. The great orthogonality theorem or the wonderful orthogonality theorem. And the theorem basically was about representations, basically expressing some kind of linear independence among the representations. So it says sum over all group elements G d alpha I L G d beta mj G inverse. This sum over all the elements of G gives delta Ij delta ML. So I has to match J, M has to match L, and the representation has to be same actually. So this is for irreducible representations. So where n alpha is the dimension of the representation alpha. And by that actually we mean that d alphas are n by n, okay, matrices. And then for since representation can always be chosen unitary, so after choosing the rep unitary, which is always possible, this we had proved as a separate theorem. We get sum over G d alpha I L of G, and basically the representative matrix of G inverse would have to be the inverse matrix because it represents the it's a homomorphism, it realizes whatever the group does. So the D of G inverse has to be same as D inverse of G, but since it's a unitary representation, D inverse is simply equal to complex conjugate, transpose complex conjugate. So djm beta star of G now, okay. So that is equal to these things, okay. So we bring forward the order of G, size of the representation, and delta alpha beta, of course, that's why we can just put either alpha or beta there, it doesn't matter, and then delta Ij delta ML. Still it is tied across, but this is what it is. Now the next thing we will do is to convert this into a relationship for the characters. So this is for the matrices themselves, all the representation matrices themselves, but we can now convert it into an identity for the characters. So to convert into an identity, or rather a formula for a relation for characters, note that we need to trace this. So we need to sum over I equal to L and separately sum over j equal to m. Right? That is what tracing would require. That will produce traces on the left hand side if we do this summation. So on the right hand side, by the way, this RHS, LHS is very, very English, okay, British, and in India it is extremely common. You go to America, people will say, what is LHS? So you have to every time tell them that LHS means left hand side. Okay. So it's not a standard convention everywhere in the world. They will really ask you. Every single time that I try to say this, I get asked. So on right hand side, if we do this, so sum over I equal to L, sum over j equal to m of, now what is there on the right hand side? Well, these are things independent of I and j, but if I put the things that are dependent on I and j inside, then I have this. But if I do a summation mj, then I am summing this and this, but that is like matrix product of this delta with this delta. So it actually results into I equal to L. The outer summation is still there. The inner summation has simply produced delta IL. Right. But the sum over delta IL only gives me n alpha, because that is the trace of the identity element, which is size of the representation. Is this clear? So this is the identity is an n alpha by n alpha matrix, so it is equal to n alpha. So if we now carry it here, then this summation has given us n alpha, so it will just basically cancel this n alpha, and we get a much prettier looking relationship which simply says sum over all group elements G d alpha, sorry, chi alpha, sum over all G. By chi we mean the character for the representation alpha of element G, and then chi beta star G. This is simply equal to size of G, order of G times delta alpha beta. So this is much more like a orthogonality relation. So this is as if we have vectors chi whose size, or vectors chi which live in dimension equal to the order of the group G, because so if you think of G as a component of chi, or entry chi as a column vector with entries in it, there are as many entries in the column vector as there are elements G. So chi can be thought of as a mod G dimensional vector. As a column vector with rows labeled by elements G. Such a vector is same dimension as the order of G. So, one thing becomes clear, it is difficult to have too many representations, because as vector, so suppose alpha and beta, there were large number of them, very large number of them, but then their dimensionality is restricted to mod G. So obviously you cannot have orthonormal vectors, mutually orthogonal vectors that are larger than the order of the group, right. In fact, the relationship is tighter, so this limits possible irreps. Remember, the whole thing is derived only for irreps. It's the relationship is for irreducible representations. If you want, we can write it here. So this limits possible irreps, possible number of irreps alpha, alpha beta, because you can't have indefinitely large number of them, because you will not be able to produce so many independent vectors. The relationship is also sometimes written. By now we remember that the characters in a particular conjugacy class are the same, because under conjugate transformation the trace doesn't change. So characters in a conjugacy class are all the same. So all G belonging to conjugacy class Ci. Then let Pi be number of elements in Ci and how many conjugacy classes, that also we can introduce a symbol for. So we are just going to rewrite this summation for directly for conjugacy classes. So let Pi be the number of elements in a class Ci, and let there be totally, so we can now look at this. This summation will break up into summation over classes, and when you are summing over a particular class, the value of chi will remain the same. So if there are elements P in that class, then all we need to do is put Pi as the weightage factor. So this relation becomes R independent classes. They are of course independent, as you know, because the classes are found by an equivalence relation. An equivalence relation produces disjoint subsets. So therefore we can thus we can also write sum over the conjugacy classes I, Pi and chi I alpha, chi beta star I this equal to modulus G. So now this summation is over I. Modulus G times delta alpha beta, so mod G only meaning order of G. And this summation goes over R. This again is like a inner product, but with some weightage factor. Sometimes you can, so you can have an inner product where you just multiply the components, but sometimes you can have an inner product where there is a weightage associated with each of the components. It's sometimes called a metric. So you could just put weightage factors and think of this as a more general orthogonality relation, or you could just redefine the chi tilde to be square root p times chi. Okay. This is a temporary thing, we are going to other topic, but just as an end comment on this writing, redefining chi tilde alpha to be equal to square root pi times chi alpha, we find we have I, summation is over classes going up to R, and simply chi tilde alpha I, chi tilde beta star I equal to mod G times delta alpha beta. So we actually have a more strict constraint on how many alpha beta we can have, because we can now earlier I was saying there are as many components to chi as there are elements G, but to chi tilde there are even fewer components, only as many as there are classes. Okay. So in fact the total number of representations, irreps, will be restricted by how many classes there are. You can't have indefinitely large number because you cannot produce so many independent orthogonal vectors. You are living in a dimensionality that is only R, you can't produce more than R dimensional vectors. So thus the restriction on number of irreps is stronger sometimes people write number of irreducible representations to be rho. If there are rho irreps, then above orthogonality means, I try to write this out because if you later read the notes, if I just jump to writing the equation, then the continuity is lost. So at the risk of spending a little more time, I just write this down. Above orthogonality of chi tildes means that rho is less than or equal to R, where R is the number of independent classes. So there is a natural restriction. So in fact it is also possible to prove the opposite, namely rho can also not be bigger than R. Rho can also not be less than R, or rather the so there is another orthogonality which we will not prove because it takes a little time and just gets more formal, but it is possible to prove where the summation is over the representations, going up to rho of chi I alpha chi j alpha star equal to so we will not prove it here. So this then restricts the number of classes to remain less than the number of representations. So putting together the two inequalities, rho less than equal, yes. See, so let me, so do feel free to ask a question, because in fact that helps me sometimes to clarify if anything got left out. So the Ci are conjugacy classes. The subject is abstract enough that it is going quite fast, and if you have a question even at the cost of repeating something, I don't mind saying it again. Okay. So there are conjugacy classes in a group under conjugacy transformation, which is like a similarity transformation in matrices, and the character is nothing but trace. So trace remains unchanged under a similarity transformation. So all elements within a conjugacy class, was that the question? So that is all you are asking. That should be size of the, so there is some redundancy of notation. We should put R over there, right? The number of elements in the, for that we have a notation, number of pi, not Ci. Number of elements, thank you, that's all you are asking. Number of elements in the conjugacy class. Okay. Now we prove using this orthogonality. We have another interesting fact. So this is sort of end of up to this point. Now we convert this orthogonality into a more powerful tool. We can analyze any representation. So now somebody hands you a representation and you want to know whether it is an irrep or not. Somebody just gives you a representation that this is a representation. You can check that it is a homomorphism by checking that the group table comes out the same. But how do you know if it is an irreducible representation or not? So this orthogonality actually even allows you to analyze, because of it's a linear kind of relation. So you can split up a given reducible or arbitrary representation into irreps by using this method. Utilized for resolution of arbitrary representations. So suppose we are given a generic representation D such that D of G is equal to, and the way we write it is D1 G plus, so it is a direct sum. Where di or d alpha are irreps, and this means direct sum. We rewrite this as equal to sum over alpha, and alpha we have said that let there be row number of irreps, so the sum goes over that, and a weightage factor m alpha times d alpha G, where technically I should have put here not ordinary sum but actually the group theory sum, the linear okay. So suppose you are given some arbitrary reducible representation. Now the trick to play is to simply take trace of both sides. So if you take trace of both sides, then you basically get trace of the arbitrary rep, but on the right hand side you get traces of individual irreps, but those chi alpha form a vector space which are orthogonal. So you have essentially resolved a chi in arbitrary representation in that. So taking traces on both sides, we write this relation as chi, and we put a d to put, say that it's some generic rep, it's not alpha, it's not labeled by the index of this. So we say that this for any element G is going to be summation over alpha equal to 1 to rho m alpha, and basically character of the representation alpha, character in representation alpha of the element G. Okay. But now you can multiply by chi star beta on the right and sum over G. So resolve into components by, say, multiplying by chi star beta on the right and summing over G. Actually that should have gone inside, but doesn't matter. M alpha but that produces delta alpha beta. So that just actually becomes So that produces a G times delta alpha beta. So we can, that basically collapses this summation over alpha to just being m beta. So that implies m beta can be extracted as 1 over order of G sum over G chi d right. This is also for G. So this is a clever thing that one can do. One can identify the weightage of any rep in the general reducible representation by simply projecting out onto the chi beta basis. So now we have proved that I can extract the m alpha for anything. There is another relationship we can derive, an important theorem actually using this.